get started with introducing our next speaker. Yanai leads data science for Meta's data center end-to-end lifecycle. He oversees data engineering, business intelligence, advanced analytics, and engineering solutions for global data center planning, build, and operations. He spent time at Verizon supporting supply chain operations, procurement, and real estate. Held several leadership roles there. And is an LGO alumni, the program that a lot of us are in. So we're really excited to hear from him.
Okay. First of all, thank you for hosting me. It's great to be back. It's been a while, especially with the pandemic. And it was good to see Professor Ramakrishnan talk about, he actually started by saying like how Meta or Google, Amazon has all this great labeled data. So, yeah, so, but that's what my peers have when they are on the product and consumer side. And I'm on the operational data center side, so I actually get to deal with everything he discussed. So we actually have, what he said, it might take some time to get it operational. We actually are operationalizing some of it right now. So it was great to see what he was talking about. But before we talk about those use cases, let's start. Today we'll talk about machine intelligence in data centers operations at scale. And not many people realize, but that's actually a massive amount of what we do. So I'll start back to talking about the data center industry as a whole. Where does data science come into it? Where does analytics play to it? To how do we even decide on what to work on? And then I'll cover a few use cases. I think we already discussed, shared my background. Excited to be here, but also I appreciate the fact that I had a chance to do both the operational side, engineering side, and now looking at it from a data science perspective, it helps me, like Rama described, really understand and work with the SMEs to help understand the data and what they're looking for and how to make it usable for them. So let's talk about the data center industry and why is it important for operations and manufacturing. I'll start with a few tidbits around it, or what it even is. If you think about probably anyone who is on the phone right now is probably using a data center somewhere in the world. Because what's effectively, it's a computer somewhere else that's running and processing or storing everything that we do over the web. In Meta use case, of course, if you use WhatsApp or Instagram or Messenger or Facebook, you're probably connecting through it. We have a lot of data centers around the world. That's global. That's not only Meta. Thousands of them. And each one is several football fields in size with tens, sometimes hundreds of thousands of computers and machines. Just to get a sense, it's about close to $250 billion of spend annually, globally, on data centers. That's about the budget of Mexico or Sweden. About 1% and expected to go to 3% in the coming years of the world electricity actually goes to data centers. That's give or take about how much the United Kingdom is using in their electricity, just for data centers. And the other thing I like interesting is the amount of storage data, the 2.5 zettabytes. That's about the entire internet traffic in 2021, while we were all at home. Is that amount of data that we take all in. So how it works, and quite clearly, every time you use any type of app on your phone, you connect with a general service provider, if it's AT&T, Verizon, or any international area. Global subsea cables, internet cables, it goes all the way down to a data center. In the data center itself, we have a single server, usually in a rack, that goes into a data hall. And that's really what this big, massive places are composed of. Millions and millions and millions of those rows of servers and machines. And if you think about it, those things are have a tendency not to operate at scale and continuously running nonstop. You need to think about what kind of technology you put there, what's coming in, what's coming out, how to operate, how those things tend to fail over time, how do you ensure that you have the right humidity control, the right temperature, the right amount of power. it's actually quite unimaginable, but those things can actually blow up. The amount of heat they generate is enough to keep the place heat on itself, and you need to control that heat as you go. So before we think about applying data science, we need to understand the data center life cycle of how it goes. Well, we actually plan where and how much and many in the world capacity do we need. So if we want to run compute or data storage, what kind of equipment or power you need and where in the world are you going to build it. For that, you need to design both the servers or the racks, but also the building itself, which is a very smart building. It's almost, if you ever walk inside, it's like you take an air conditioning unit and blow it up to a size of a football field, and you are walking into it. And it self-controls the entire environmental conditions around it. You have the entire build of it, which, again, a lot of people are not aware, but we actually build our own data centers. So we build it from the ground up, all the way from breaking ground to doing the foundation for the entire network, cabling, power, water, and standing up the entire building. Running for the operations of the moment you finished it, you need to turn it on and have the racks and servers, logistically, spare parts, material, network connection, electricity, maintenance, generator maintenance, and of course, server maintenance for it. And finally, every time a new technology comes in, you need to either retrofit it, either upgrade the network, change the computers, or just decommission it and move to something new. For that, we really have data science in all parts of the, or machine intelligence in our case, all parts of the data center lifecycle. Looking at when is the optimized time to turn up or to introduce a new technology, and what is the optimized way to allocate services, hardware, network, etc. In the design phase, you always need to cut the balance between power, heat, capacity or efficiency, and a lot of simulation of what will happen. There are questions of what's the size of a corridor you need to have in order to allow the right throughput of things coming in and out. On the build side, we have a lot of interesting, and that's actually a good application of what Professor Ramakrishnan just explained, where if you think about when you finish building a data center, you generate a significant amount of certificates, documents, manuals, and then you need to pass it to the operating team in order to validate it. And it actually becomes tens of thousands, in some cases millions of documents. Auto-classifying it, so this goes to electricians, this goes to mechanical, this goes to hardware, and also auto-labeling it and ensuring that, hey, this is probably something you should look at, and this is something we can automate. That's exactly where the kind of technologies that were described earlier apply. And that's what we are doing in practice. Right now, we are auto-labeling those thousands of documents and finding errors and problems and quality issues in our build through that automated machine learning. On the operation side, and I'll touch about some of those use cases soon, we need to both understand if server failed, what's wrong with it, continuously optimize our operational conditions in the data center, predict equipment failures, and the regular supply chain and spare parts management. And in the retrofit and decommission phase, there's the continuous decision of when is the right time to do it. And this is really just another representative list of many applications that we have through the entire process. But before we even go and start working on those things, the question that comes up is, okay, where and how do we decide what to work on? And there's a very important phase of analytics around it, which looks at our data centers and a framework where we created about who really cares about the work. And we don't do machine learning or machine intelligence for the sake of doing machine intelligence. We do it in order to create value to something for the reason we have data centers in the first place. And that's a framework we tried to build here, where we start, well, we have our direct customers. If you think about like an Amazon AWS, it would be whoever is using their data centers for getting their capacity or compute. In our case, it's more for our internal apps. The owners or the shareholders to ensure that we are actually running it in an operationally efficient way. So we are not just wasting energy or wasting power or wasting compute, we're actually getting something out of it. Or the performance, so if we build X amount of capacity, what percentage of that are we actually utilizing effectively? And as important, we need to look at the environment or the communities or our employees who actually are in those locations all around the world, and making sure we are doing the right thing. Renewable energy, and making sure and thinking about the environment and communities we are creating, the job prosperity, and the goodness we can create to the environment. So that high-level framework really resulted in us evaluating everything at the top, from either capacity we are delivering, how well we are performing the capacity, how operationally efficient is that capacity is, and the responsibility we have around it. But we didn't only want to keep it at the top level, we wanted also to tie down to the work happening at multiple levels, both at a strategic level, so different areas that it can actually impact, well, what is our capacity plan in a strategic level, what is our server availability, so percentage of servers that are available to run traffic, or what is our capital expenditure, so how much capital are we spending for every kilowatt or megawatt we are creating. And then looking at our community impact or net zero carbon footprint, etc., which we have commitments on. So that's on the strategic level, but we also wanted to go several levels deep. What is driving strategic? I'll give one example on part availability. Server availability comes from how much parts you have actually available, which comes into supply chain. So you actually are able to tie all the way up to the biggest impact of, hey, what is our server availability for people that are fixing servers right now, or ensuring that we have the right amount of parts. I'll focus on PUE and WE because that's actually a very important metric in the data center industry. It looks at, when you want to know how effective you are in your data center, you need to look how much power are you spending on the data center in general, divided by the power you're actually allocating to compute or storage, or IT power. Ideally, you want that number to be 1. That would be perfect. So you're not wasting a single watt of energy on anything else. The reality is that you need to keep it either cool or hot, and you need to make sure that people can actually operate in that environment, and there's peripheral and overhead equipment. We've been optimizing that for a while. If the industry is running at around 1.8, 1.6, we've been running at 1.1. So that's definitely an area for us. Same goes with water. You want to really use a minimal amount of water compared to the capacity you're creating. And how do we actually do that? And that's where machine intelligence comes in. If you look at this yellow line, or maybe let's start with the Y and X axis. If I think about our data centers, it's almost like an operating envelope. There's the amount of power you put in and amount on cooling capacity you have. So how much literally fan power you can allow in order to keep the place cool. So clearly, the more power you put in, think about like a computer that heats up, the more the fan needs to run harder. And you have a max amount of cooling you can do and a max amount of power. And in a linear system or a naive system that runs most buildings, even probably the air condition here in this building, well, X amount of power, X means Y amount of cooling, fan running. And that's regular building. Well, by using reinforcement learning, we are actually trying to continuously learn what is the optimal amount of cooling we need per the amount of power, and it's non-linear because there's many other variables in the environment: humidity, the temperature outside, the different distance and pressure, etc. All of that leads us to create an optimal continuous curve that keeps getting feedback from the environment as we go. Okay. Let's talk about a few use cases. Let's start with predicting hardware remediations at scale. So if you think about when you have millions and millions of servers, like any computer or any hard disk or memory disk or motherboard or CPU, they fail at some rate. And when you have millions of them, you have a lot of failures. And when you think about you have data centers all around the world, that's where our technicians spend a lot of time. They need to go to a certain row and a certain data hall and go to a specific server, pull it out, and figure out what's wrong. The good news, and that's very common, there's automated tooling, software, that tells you, hey, I'm talking with that server in row 2B. You should probably look it up and see what's the problem. And hey, it looks like the hard disk is failing. So that's ideally, and then you don't need theoretically machine intelligence. But the reality is that we keep updating our hardware and software and firmware and the different ways we do. So what's actually happening is not only that our technician time is spent, but our engineering time is spent on keep updating those tooling. Where by the time we update the tooling to tell, hey, if it's error log XYZ, it means that you need to replace a CPU. By the time we figure that out, got the feedback back from the technician, put that in the tooling, we already updated our software and hardware again, and then we need to, there's a time lag on the entire software engineering process. That's really where machine learning comes in. Where if you think about that entire cycle that can take sometimes several months can be replaced by a machine learning agent that continuously understands what is a technician doing, what is resolving the ticket, and understanding what am I hearing from our servers. So again, going back, we actually are, this is like how Professor Ramakrishnan talked about the Bert and Roberta are really good on natural language. Here we're actually looking at logs, so machine logs, which is a bit different. So we actually tried BERT, and it didn't work that well. So we ended up going with something more that we developed internally that is more structured to look at somewhat semi-structured data or text that's coming from computer logs. Some of it was written through comments of people, some of it coming from like random numbers that the machine may be generating. And that, through that process and learning whatever we know about the machine and as much data as possible, we are able to predict when a server fails what is actually the problem, and teach back the software possible. So for that, in the last year or so, we were able to almost cut in half the number of undiagnosed tickets, which are usually the biggest problem. The tickets that the software doesn't know what the problem is. And our technician needs to go in and figure out, okay, is it the motherboard, the CPU, the hardware? Maybe I just need to reset the computer or update the firmware and get it done. So both an impact on our time of labor, the parts, and the availability of our server fleet as a whole, going back to that framework. I'll give another use case, and this is an interesting one. Tomorrow, actually, in the seminar, in the mimo seminar, our lead operation research data scientist is going to go into this in detail, but I'll give the high-level problem of what we are seeing. So we have, if you remember in the life cycle, we need to allocate different type of racks or different type of servers for our data centers. The way it works is that we have power units. So let's call this power unit A and power unit B. In each power unit, it can be a mother switchboard or some kind of a power line. We connect a set of racks. And racks or servers have different type of usage. Some are for storage, some can be for CPU, some can be GPUs. So each one has its own set of use cases that help solve in your set of web applications, either for external or internal. And we have many of them. But the reality is that this power unit, one, it may go down because, I don't know, there's an outage, or you actually need to do maintenance on it, which is actually required. If something is running at high voltage, you need to periodically take care of it. Well, in order to take care of it, you immediately shut down this set of servers. So if this is the allocation where we have 3 of type 1, 5 of type 2, and 1 of type 3, but on another power unit we have a different configuration, really in order to continue the operation running, you need to hold always a third power unit with a max amount of all the other power units. So you can, at any given point in time, take any one down without interfering with the production operation. So in this case, we have 13 racks. Now, ideally, if we could have allocated it differently, where we have a uniform spread of our hardware, then if you remember here we had 13 racks, in that uniform, we actually need only 9. In that one extra, that this is theoretically waste because we don't need it on a regular basis. It's a disaster recovery buffer. So we are spending significant amount of energy or power and capacity for buffer, which actually optimization can optimize. Now, theoretically, we say, oh, there's a simple solution, just uniform it all. The reality is that there's also a set of other constraints, especially new technologies. So it's not that we set it all at once at the same time. Those things continuously come. So you continuously build new data centers, you continuously build new power units, and you need to allocate the servers as you go. So it's continuous optimization happening. And there's also, of course, labor capacity of how much you can apply, and time and space consideration, supply considerations, and maintenance. So effectively, what we've been doing is running a continuous optimization of how to allocate those racks using optimization models. Mixed integer programming, which look on a periodic basis, given the current state, what's the best way to both optimize for new incoming and for rack moves. So in some cases, we actually can move racks around, if you think about like a Tetris, to get to that optimal spread. Both saving in power, in cost, and in impact. Tomorrow, Hong Bu from my team will actually talk in much more detail about the optimization model and what we do there. Cool. Okay, going to the third use case, in that one, I'm actually happy that we are actually collaborating with MIT. It's a joint research initiated. Yiding, I think, is here. Postdoc currently in course 6. And Professor Michael Carbin, Professor Hoffman from Chicago. Well, I'll set up the problem by saying, probably you've all experienced a situation where either on your computer or your phone, you just try to run an app or you try to open a page and you have this wheel that is spinning. And that wheel, and sometimes you say, I'll let it run a few more minutes, or sometimes you give up and you restart. You close and you restart the application. Well, that's somewhat tolerable when it's only my phone. But when you have millions of servers running billions of jobs, making that decision of should I let it continue running or restart is actually quite costly. Well, how costly? If you look at this graph, this is different job types represented. This is actually actual data. If you look, job type 2, the dark blue represents 1% of the longest running jobs. And they actually take about 78% or 22% of our compute power. So 1% of the jobs take 22% of the compute power. So if we knew ahead of time about them, maybe we're much better off actually restarting them for the long term. And that's exactly the question we are trying to answer, and it's actually quite hard. It's asking two questions. One, before the job starts, usually 24 hours before, that what we are doing now is, are we able to predict if something is going to be a straggler? Is going to take that longer time? What we also want to be able to do is, during the run, ask ourselves, am I going to be a straggler? So am I a straggler right now? Am I just holding up the system and I should reset? So trying to get those two as we go. For the concept we are doing, now we are really applying classical machine intelligence and doing all the data labeling and data prep around it in order to predict that 24 hours in advance. I'm also very excited about the novel approach that the team here in MIT is looking on, asking yourself on negative unlabeled data. So I'm still running, it's still negative, but it's unlabeled to answer, am I a straggler right now? The actual, in practice, what's happening is we are missing data to know enough about the job while it's running to do that yet, but we are hoping to get there as well. And clearly the impact here is getting capacity back into our fleet, and that it's available for us to actually run other applications compared to just having that spinning effect. Cool. I'll stop here and open up for any questions.